Yo, 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 yo! So mag-discuss ulit tayo ng panibagong topic tungkol sa fluid flow on closed conduits. So nung last time na-discuss natin, yung tungkol sa velocity distribution in pipes. Ngayon naman ay pag-usapan natin yung tungkol sa head losses in pipes. Alam ko na-discuss na natin to dun sa previous topic natin about flow and energy in fluids. Pero ngayon ay himayin natin kung paano ba natin mako-compute yung head losses sa isang hydraulic system, lalo pa kung yung fluid is flowing in a pipe system. So gaya na nabanggit ko noon, ang other terminology natin for head loss ay pressure drop at binabawas natin ito sa input energy head. So by definition, head losses are the energy losses in a hydraulic system due to frictional resistance. So due to some factors, mostly properties din ng pipes, ay nagkakaroon nga ng head losses. Pero bottom line nito ay dahil talaga ito sa frictional resistance. Kasi meron tayong pipe and inside the pipe there is a flowing fluid. Siyempre kung flowing yan, merong flow rate and pressure na pinaprocess yung fluid. At since flowing nga yung fluid sa pipe, so may portion ng flowing fluid wherein may contact dun sa pipe walls. And due to that contact, alam naman natin na two particles or objects or matter that are directly in contact to each other causes friction. At depende kung anong type of material yung pipe ay nagva-vary din kung gaano kalakas yung magiging resistance nung pipe dun sa flowing fluid in terms of energy head due to friction. So kung i-illustrate natin yung nangyayari sa energy grade line kapag ka flowing yung fluid, kasi meron na lang pipe at inside the pipe there is a flowing fluid. So meron yung flow and pressure. So maglagay tayo ng piezometer sa sinet nating points 1 and 2. So at a certain run of pipe ay bababa ang energy grade line. So it is sloped down at yung energy head from point 1 to point 2 is being decreased. So yung difference ng energy grade from point 1 to point 2, yun yung head loss due to pipe friction. So kung wala tayong i-consider sa system, then we conclude that the system is ideal. At since wala naman talagang ideal na system in actual, so theoretically lang siya mangyayari. Kaya in actual application, like engineering design, ay talagang i-consider natin itong mga head losses out. Kasi talagang may encounter yan sa system. So for a non-ideal system, then E sub 1 minus yung total head loss na may encounter dun sa system equals E sub 2. Then E sub 1 minus E sub 2 is equal to the total head loss. Since ang input energy head nga natin ay from point 1, syempre magdi-decrease yan, no, due to head loss. Kaya nga, immediately, binabawas na agad natin itong total head loss na to. So meron tayong two major classifications for head losses sa isang piping system. At yun ay yung major head losses at yung minor head losses. So kapag sinabi nating major head losses, kaya nga siya tinawag na major head losses, ay siya mostly yung nagko-contribute ng may mataas na value ng head loss sa system. And major head losses come from pipes. So gaya nga na nabanggit ko, depende sa material ng pipe yung makukuhang head loss sa system. Kasi may iba't iba tayong material for pipes, merong plastic, may gawa sa metal, at lahat ng pipe materials na to ay magkokos ng friction sa flowing fluid. So, sunod naman ay yung minor head loss. So, yung minor head loss naman ay yung mga head losses na caused by other components in the system rather than pipes. So, usually, yan ay caused by pipe size enlargement, pipe size contraction. Kasi sa isang hydraulic system naman ay hindi naman yan uniform lang yung magiging pipe sizes. So along the run ay hindi natin maiwasan na mag-reduce or mag-increase ng pipe size. So another cost of minor head loss ay from fittings, no? Gaya ng bends, T, and other kinds of fittings and some components and appurtenances gaya ng iba't ibang klase ng valves. So, makaklasify o may isa-isa natin yan sa water supply engineering. And for the meantime, binibigyan ko lang kayo ng idea kung ano ba yung magkokos ng mga minor head losses na to at kung paano rin natin siya mako-compute. So simulan natin yung discussion for the formulas of head loss sa major head losses. So lahat ng gagamitin nating formulas dito sa major and minor head losses are mostly from empirical formulas. Ibig sabihin, na-come up yung mga formulas na to through experimental procedures. At para dito sa major head losses ay merong tatlong empirical formulas tayong gagamitin. So itong mga formulas na to yung ginagamit na rin natin for engineering design na pwede natin magamit in actual practice. So yung una na dyan ay yung Darcy Weisbach formula. So this formula is named after Henry Darcy and Julius Weisbach. So they are both European scientists and engineers that gave contribution to fluid mechanics. So yung general equation for Darcy Weisbach formula is H sub F. So ito yung gagamitin nating denotation para sa major head loss. H sub F, that is head loss due to pipes friction, is equal to F L over D times velocity head or V square over 2G. Wherein F is the friction factor or sometimes called as the Darcy friction factor. So unitless yan. At hindi constant ng F. So nakadepende pa yan sa characteristics ng pipe gaya ng diameter, yung roughness height epsilon na later on madidiscuss natin mamaya, at dun sa viscosity ng fluid. So pwede nating ma-determine ang value ng F through some formulas. Also pwede natin siyang ma-determine gamit yung tinatawag na Moody diagram. So discuss pa natin yan later on. So yung L is the pipe length, so it's in terms of meters or feet. D is pipe diameter, so that is in meters or feet. So ang tinutukoy natin ditong diameter ng pipe ay yung inside diameter, and yung nominal diameter naman talaga ng pipe is always the inside diameter. So V is the average velocity or flow velocity in meters per second or feet per second. Then G is the acceleration due to gravity, so that's 9.81 meters per second square for SI, and for English that is 32.2 feet per second square. So ngayon pwede pa nating i-modify yung formula. So what if Q yung given na data at hindi mo na gagamitin yung formula na Darcy Weisbach formula of head loss na in terms of velocity. So yung velocity head dito na V square over 2G ay pwede nating palitan nung ginagamit nating formula na 8Q square over pi square G d raised to 4. So once na masubstitute na natin ito sa formula, ay pwede natin nang i-compute yung constant value dito, which is 8 over pi square times G. So ngayon, gamitin natin ay yung G for SI. So that is 9.81 meters per second square. So yung makompute natin na constant value is 0.0826. So yung magiging formula na for Darcy Weisbach formula for head loss in SI na in terms of Q is HF is equal to 0.0826 F times L times Q square all over D raised to 5. So take note lang na yung Q dito should be in terms of cubic meters per second since for SI units nga yung formula. So ganun din ang gawin natin para sa English units. So gamitin pa rin natin yung HF is equal to F L over D times velocity head na in terms of Q or 8Q square over pi square G d raised to 4. So para naman dito sa English units ay ibahin natin yung value ng G. So gagamitin natin yung value na 32.2 feet per second square at computein ulit natin yung value ng constant. So ngayon, ang makakompute natin is 0.0252. So, ang magiging formula natin would be H sub F is equal to 0.0252 F L Q square over D raised to 5. So, yung makakompute natin dito na H sub F ay in feet. Then, syempre, gagamitin natin ditong L and D ay in terms of feet din. So, yung Q naman na gagamitin natin for this formula should be in terms of cubic feet per second. So tulad ng sabi ko kanina, na yung value ng F is characterized by some factors gaya ng pipe diameter and the roughness height epsilon, then it can also be characterized by the viscosity of the fluid and also the velocity. So pwede ring dumepende ang value ng F sa characteristics ng flow nito. Iba yung value ng F kapag laminar yung flow, iba rin yung F kapag turbulent naman yung flow. So ngayon, pwede nating ma-derive kung ano ba yung value ng F kapag laminar yung flow. So kung maalala nyo, may na-derive tayong formula nung last time na centerline velocity na in terms of head loss din. Na kailangan nating magamit na formula dito ay yung mga factors nga na naka-affect dun sa F. So, which is, nandito na sa formula na to, yung velocity, yung head loss, as well as yung viscosity. Pero, hindi naman natin gagamitin dito yung centerline velocity at yung average velocity lang yung nasa equation ng Darcy Weisbach head loss formula. So, yung mga working equation natin dito would be V sub C or centerline velocity is equal to gamma times H sub L times R sub O square all over 4 times L times mu. So, para naman dun sa average velocity is equal to 1/2 centerline velocity. Gaya nga ng sabi ko, dapat natin matranslate yung centerline velocity into average velocity. So, yung magiging working equation na is V or average velocity is equal to 1/2 times the quantity of gamma times H sub L times R sub O square all over 4 times L times mu. So, multiply natin yung mga constant dito. So, that would become V is equal to gamma times H sub L times R sub O square all over 8 times L times mu. So, ngayon, at since yung formula naman natin, dapat talaga dito ay in head loss. So, i-modify natin later on yung formula na imbes na yung formula is for average velocity, magiging yung equation na is for head loss na. So ngayon, ang gagawin ay medyo re-replicate natin yung formula for Darcy Weisbach head loss formula. So, expand ko pa yung equation ko. So, yung gamma o yung specific weight will be translated into rho g. Then, yung R sub O ko o yung radius ng pipe would be translated in terms of diameter. So, that would be D over 2. So, yung maging resulting equation na would be V is equal to rho times G times H sub L times the quantity of D over 2 square all over 8 times L times mu. At since re-replicate nga natin yung Darcy Weisbach equation ay dapat V square yun nandito sa ating working equation. So, V lang itong nasa working equation. So, gagawin natin, multiply natin both sides by V para makuha natin yung kailangan natin na V square sa equation. So, ngayon, yung magiging resulting equation na would be V square is equal to rho G H sub L D square over 4 times V all over 8L mu. So ngayon, pagsamahin na natin dito yung constant pang value, yung 1 over 4, which is nasa numerator, at saka yung nasa denominator na 8. So, ngayon, ang gagawin ko pa dito ay paghiwalayin pa natin yung D. Kasi dun sa ating Darcy Weisbach equation, hindi naman yun D square, kundi D lang, no? So, kasi nga yun ay H sub F is equal to FL over D. So, paghiwalayin natin dito sa ating working equation, yung D. So, magiging resulting equation na would be V square is equal to rho G H sub L times D times V all over 32L times mu. Ngayon, kung iisa-isahin natin itong mga functions dito sa ating working equation, kung mapapansin nyo ay meron ditong familiar na mga functions. Gaya nitong rho, D, at saka V. So, ayun yan ay rho dV, tapos nasa denominator pa yung mu, equivalent din siya dun sa na-derive natin noon na formula na dV rho over mu, which is equivalent to the Reynolds number. At since equivalent nga yun sa Reynolds number, then the resulting equation would be V square is equal to the Reynolds number RE times D times G times H sub L all over 32L. So ngayon, pwede na nating ihiwalay yung head loss. No? Ilipat natin yung head loss sa left-hand side of the equation at yung other function sa right-hand side of the equation. So that is H sub L is equal to 32 times L times V square all over R E times D times G. So, since i-replicate mga natin yung Darcy Weisbach equation, kung papansin nyo sa denominator, G lang yung nakalagay dun sa equation. Pero ang kailangan nga natin, since ang formula nga ng Darcy Weisbach equation should be in velocity head or V square over 2G, pwede nating i-multiply both numerator and denominator to 2. So kapag na-multiply na natin both numerator and denominator to 2, then the resulting equation is H sub L is equal to 64 over Reynolds number. So ihiwalay ko na dito yung function na similar dun sa Darcy Weisbach equation. So that is L over D times velocity head. So, ngayon kung mapapansin nyo, ang wala lang dito sa ating working equation ay yung F. So, yung tinutukoy na F dito o yung friction factor para sa laminar flow ay itong 64 over Reynolds number. So, kung ito nga yung value ng F, so babalik talaga tayo dun sa equation na H sub F is equal to F L over D times velocity head or V square over 2G. So, ang conclusion natin, so if laminar flow, then the value of F or the friction factor is 64 over Reynolds number. So ngayon, isunod naman natin yung formulas for F para naman sa turbulent flow. So sinulat ko na lang siya kasi these are all empirical formulas. And for sure, hindi naman natin to magagamit halos lahat. Pero yung ibang formulas dito ay may nakalagay na condition. So para sa number 1 ay for smooth and rough pipes. So F is equal to 8 tau sub O over rho times V square, or also equal to 8 V sub S square over V square. So yung V sub S dito ay yung shear or friction velocity. So for number 2, yung condition naman is for smooth pipes wherein the Reynolds number ranges between 3,000 to 100,000. So this formula or equation is from Blasius, a German physicist. So F, yung value ng F is equal to 0.316 over Reynolds number raised to 0.25. So kapag ang condition naman is for smooth pipes with Reynolds number to about 3 million. So medyo mataas na to. Super turbulent na to. So ito yung equation, 1 over the square root of F is equal to 2 log times the quantity of Reynolds number times the square root of F minus 0.8. So pwede natin gamitin tong mga equations ito, pero sinasabi ko nga, hindi lahat ng equations ay kailangan nating i-memorize o kailangan nating gamitin. So pwede naman tayong pumili lang ng isa kung saan tayo mas komportable o kung saan yung mas madali nating matandaan. So ang sunod ay kapag ang condition ay for rough pipes wherein the value of the nominal thickness of the viscous sublayer na na-discuss natin nung last video is sigma sub T is less than 0.3 by epsilon. So epsilon is the absolute roughness or the roughness height in millimeters. So this equation is known as Karman equation. So that is 1 over the square root of F equals 2 log times the quantity of D over E plus 1.14, wherein yung value ng sigma sub T or the nominal thickness of viscous sublayer is 11.6 times V times the square root of the shearing stress tau sub O all over rho or the fluid's density. So ang sunod naman ay yung most commonly used na way ng pagdetermine o ng pag-compute ng value ng F or ng friction factor pagka turbulent yung flow. So in this condition, this is for smooth and rough pipe, then turbulent yung flow, at yung equation ay tinatawag natin Colebrook equation. So yung formula is 1 over the square root of F is equal to negative 2 log times the quantity of epsilon. So yung epsilon na tinatawag dito is the roughness height of the pipe. So ano ba yung tinutukoy nating roughness height? So kung titingnan nyo dito sa illustration, sa left side, ay meron tayong minagnify, no, na super magnified na portion ng pipe wall. So kung titingnan nyo, merong nakalagay na call out dito na protuberance. So yan yung nakaprotrude na material doon sa pipe wall that causes roughness. So yung height ng mga nakaprotrude na yan, no, so maliit lang naman talaga siya at hindi naman talaga siya makikita. So from our own vision ay makikita lang talaga natin sa pipe ay smooth siya. So ngayon yung height nitong protuberances na to ay yung epsilon, no, or yung roughness height. So ngayon nire-ratio yung epsilon to diameter, wherein pwede nating magamit yan, yung relation na yan between epsilon and diameter kapag gusto nating i-plot dun sa tinatawag na Moody chart yung value ng F. Kasi itong Colebrook's equation is plotted into a graph na mas kilala natin sa Moody chart. So ito yung madalas din na ginagamit in practice, no, para ma-determine nga yung value ng F. So kung titingnan nyo dito sa figure ay merong ang kailangan nating data para ma-determine kung ano ba yung value ng F ay yung relation between epsilon and diameter or epsilon over d, yung Reynolds number ng flow, and with that, pwede na nating malaman kung ano yung value ng friction factor F. So, bigyan na lang tayo ng example problems para mas maintindihan natin kung paano mag-plot using Moody chart. So, ang tawag nga pala natin dun sa ratio between epsilon and the pipe diameter is the relative roughness. So, yung last formula naman na yung Haaland formula by S.E. Haaland. So, similar lang din siya halos dun sa Colebrook's equation, that is 1 over the square root of F is equal to negative 1.8 log times the quantity of 6.9 over a Reynolds number plus the quantity of the relative roughness ratio epsilon over d over 3.7 raised to 1.11. So, ito yung Haaland formula na halos kaparehas lang din ng Colebrook's equation. So, yun. Yun lang para sa video na to. Sana may natutunan kayo at see you sa next video. Thank you so much.